Dear student, today we'll discuss on testing the linear equality restrictions of a regression model. Some economic theory may suggest that the coefficients in a regression model satisfy some linear equality restrictions. For instance, let us consider the following Cobb-Douglas production function. yi is equal to beta 1 x2 to the power beta 2 and x3 to the power beta 3, where y equal to output, x2 equal to labor input and x3 equal to capital input. Some of the features of this production function are it is homogeneous of degree beta 2 plus beta 3. In the special case of beta 2 plus beta 3 equal to 1, it is linearly homogeneous. The exponent of each input variable indicates the relative share of that input in the total product. Alternatively, the exponent of each input variable as the partial elasticity of output with respect to that input. The isoquants of this function are negatively sloped throughout and strictly convex for positive values of labor and capital. A function is said to be homogeneous of degree R if multiplication of each of its independent variables by a constant j will alter the value of the function by the proportion j to the power r. That is, if f of jx1 comma dot dot jxn equal to j to the power r function of x1 dot 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 xn. That is, if we can factor out j from that function, then j to the power r will be considered as the degree of homogeneity of that function. In general, j can take any value. However, in order for the above equation to make sense, f of jx1 comma dot dot comma jxn must not lie outside the domain of the function f. For this reason, in economic applications, the constant j is usually taken to be positive, as most economic variables do not admit negative values. So let's assume that q is a function of k and l equal to 10 k to the power 06 l to the power 05. Multiplying both inputs by a constant j, we get the following expression: q jk comma jl equal to 10 jk to the power 0.6 jl to the power 0.5 equal to 10 j to the power 06 k to the power 06 j to the power 05 l to the power 05. Applying the index rules, so we can group the exponent of j to the power 0.6 plus 0.5 into 10 into k to the power 6 l to the power 0.5 equal to j to the power 1.1 into this expression gives us q as a function of k and l. In our Cobb-Douglas production function, x2 and x3 are two independent input variables. Now, if j is any constant greater than 1, then our production function will be homogeneous of degree beta 2 plus beta 3 if we have the followings: beta 2 into jx2i to the power beta 2, jx3i to the power beta 3 equal to beta 1 j to the power beta 2, x2 I to the power beta 2, j to the power beta 3, x3 to the power beta 3 equal to j to the power beta 2 plus beta 3 into beta 1 x2 to the power beta 2 x3 to the power beta 3 equal to j to the power beta 2 plus beta 3 into yi. Therefore, our Cobb-Douglas production function is said to be a homogeneous function of degree beta 2 plus beta 3. It is noted that the exponent of j determines the degree of homogeneity. The Cobb-Douglas production function in its stochastic form may be expressed as follows: yi equal to beta 1 x2i to the power beta 2 x3i to the power beta 3 e to the power ui, where already we have learned that y represents output, x2 represents labor input, x3 represents capital input, u represents the stochastic disturbance term here, and e represents the base of natural logarithm. Clearly, in the above stochastic Cobb-Douglas production function, the relationship between output y and the two inputs x2 and x3 is nonlinear, as the parameters beta 2 and beta 3 appear as the exponent of the variables x2 and x3 respectively. Therefore, the Cobb-Douglas production function in its stochastic form does not show linear regression model. However, by taking the log transformation of the model, that is, taking natural log on both sides of the production function, we obtained the following model: log yi equal to log beta 1 plus beta 2 appears in front of log x2 plus beta 3 appears in front of log x3 plus ui. The following obtained regression model is not linear, as the parameter beta 1 appears with its log form. Letting beta naught equal to log beta 1, we have the following model: log yi equal to just beta naught in place of log beta 1 plus beta 2 log x2i plus beta 3 log x3i plus ui. Now, this model is linear in the parameters beta naught, beta 2 and beta 3, and is therefore a linear regression model. We can notice that though the model is nonlinear in variable x and y, but linear in logs of these variables. Look at these variables log yi, log x2i, and log x3i. Previously, they were nonlinear. In short, this model is called log-log or double log or log linear model. The properties of the Cobb-Douglas production function are quite well known. Beta 2 is the partial elasticity of output with respect to the labor input, as x2 represents labor. That is, if it measures the percentage change in output for say a 1% change in labor input, holding the capital input constant. Likewise, beta 3 is the partial elasticity of output with respect to the capital input, holding the labor input constant. The sum beta 2 plus beta 3 gives information about the returns to scale, that is, the response of the output to a proportionate change in the inputs. If this sum, that is beta 2 plus beta 3, is equal to 1, then there are constant returns to scale. That is, doubling the inputs will double the output. Tripling the inputs will triple the output, and so on. If the sum is less than 1, that is beta 2 plus beta 3 less than 1, then there are decreasing returns to scale. Doubling the inputs will less than double the output. And finally, if the sum is greater than 1, there are increasing returns to scale. Doubling the inputs will more than double the output. That is, in short, if beta 2 plus beta 3 less than 1, then we have decreasing returns to scale. If beta 2 plus beta 3 equal to 1, then we have constant returns to scale. And if beta 2 plus beta 3 is greater than 1, then we have increasing returns to scale. Sometimes it is very much important to find out if there are constant returns to scale or equiproportional change in output for an equiproportional change in inputs in an economic production process. Like, it is important to know whether the economy of a country is showing constant, decreasing, or increasing returns, or whether a firm is exhibiting constant, decreasing, or increasing returns to its input. Sometimes in economic theory, it is assumed that beta 2 plus beta 3 equal to 1. This kind of restriction is called linear equality restriction. Beta 2 plus beta 3 equal to 1. This shows a linear relationship between beta 2 plus beta 3. So this is called the linear equality restriction. Therefore, it is important to check or test such kind of restriction empirically. That is, we have to test whether such kind of restriction is valid or not. There are two approaches to test the linear equality restriction. The first one is the t-test approach, and the second one is the f-test approach, the restricted least squares. Our null hypothesis is that beta 2 plus beta 3 equal to 1, which states that there are constant returns to scale. Our alternative hypothesis is beta 2 plus beta 3 is not or is equal to 1, which states that there are either decreasing or increasing returns to scale, but there are no constant returns to scale. The t-test approach. Let us discuss how we can use this approach to test the linear equality restriction. Using the Wallace method, we can estimate the following unrestricted or unconstrained regression model. This model gives us the estimated values beta hat 0, beta hat 2 and beta hat 3. Under the classical assumptions and the null hypothesis of constant returns to scale, it can be shown that t equal to beta hat 2 plus beta hat 3 minus beta 2 plus beta 3 divided by standard error of beta hat 2 plus beta hat 3 follows the tree distribution with n minus k degrees of freedom, where k is the number of parameters to be estimated including the constant term, and n is the number of observation. It is noted that the expression standard error of beta hat 2 plus beta hat 3 is equal to the square root of variance of beta hat 2 plus beta hat 3. So if we expand this expression, we'll get this expression. uh, Variance of beta hat 2 plus variance of beta hat 3 plus 2 covariance between beta hat 2 and beta hat 3. Now, if we substitute the null hypothesis and the expression of standard error of beta hat 2 plus beta hat 1, our test statistics becomes t equal to beta hat 1 plus beta hat 3 minus 1. Here 1 is 1 because our null hypothesis is that beta 2 plus beta 3 equal to 1. So the denominator gives us the expression of standard error of beta hat 2 plus beta hat 3, which we have already shown that this is equal to square root of variance of beta hat 2 plus variance of beta hat 3 plus 2 covariance of beta hat 2 and beta hat 3. The substitution of the values of the terms beta hat 2, beta hat 3, variance of beta hat 2, variance of beta hat 3 and covariance of beta hat 2 and beta hat 3 from the estimated model will give us the computed t value. So these terms will give us the actual number value. Then we'll get a number value of t. Now We have to find a critical t-value for the given degrees of freedom from the t-distribution table. Therefore, if the calculated t-value exceeds the critical t-value at the chosen level of significance, we may reject our null hypothesis that there are constant returns to scale. Otherwise, we have to accept the null hypothesis of constant returns to scale. So now discuss on the F-test approach. In this approach, we will have to use two types of regression results. One is called the unrestricted regression result and another is called the restricted regression result. The t-test approach already discussed is a kind of post-mortem examination because we try to find out whether the linear restriction is satisfied after estimating the unrestricted regression. A direct approach would be to incorporate the linear restriction in the estimating procedure at the outset. We have log yi to the power log y hat I equal to beta hat 0 plus beta hat 2 log x2I plus beta hat 3 log x3I. Our restriction is beta 2 plus beta 3 equal to 1 or beta 2 equal to 1 minus 3 by rearranging this expression, or beta 3 is equal to 1 minus beta 2. Therefore, using either of these equalities, we can eliminate one of the beta coefficients in the unrestricted model. So, if we use beta 2 is equal to 1 minus beta 3, we can write the Cobb-Douglas production function with log transformation as follows. Log yi equal to beta naught plus beta 2 log x2I plus beta 3 log x3I plus ey. Now, substituting 1 minus beta 3 in place of beta 2 will get this line. Log yi is equal to beta naught plus 1 minus beta 3 into log x2i plus this part. After simplification, we'll get this expression. Log yi divided by x2i equal to beta naught plus beta 3 log x3i divided by x2i plus ui. This regression is called the restricted regression model because we have obtained this model by applying these restrictions. Beta 2 is equal to 1 minus beta 3 into our unrestricted model. This is the unrestricted model. Here yi divided by x2i represents output labor ratio as x2 represents labor and y represents output, and x3i divided by x2i represents capital labor ratio as x3 represents capital and x2 represents labor. So this kind of ratio has some great economic importance. Now, once we estimate beta 3 from the restricted model, we can easily estimate beta 2 from the relationship beta 2 equal to 1 minus beta 3. We have log yi is equal to beta naught plus beta 2 log x2i plus beta 3 log x 3I plus ui. So this model is called unrestricted model, and we have found the restricted model as log yi is equal to x2i is equal to beta naught plus beta 3 log x3 divided by x2i plus ui. So how do we compare the restricted and unrestricted least square regressions? In other words, how do you know that, say, the linear restriction beta 2 plus beta 3 equal to 1 is valid? This question can be answered by applying the f-test as follows. Let sum of u hat ur square. This term represents residual sum of square of the unrestricted regression from this regression. Sum of u hat square r equal to RSS of the restricted regressions. That is, this term represents residual sum of square of restricted model from this model. M is a term that will be used in the formula. M represents number of linear restriction in one in the present example, because beta 2 plus beta 3 is equal to 1. This term represents single restriction or only one restriction. K equal to the number of parameters in the unrestricted regression model, n the number of observations. Then the variable f, which is defined as follows: RSSR, that means residual sum of square of the restricted model minus residual sum of square of unrestricted model divided by m, number of restrictions, divided by residual sum of square of unrestricted model divided by n minus k of the unrestricted model. So this variable f follows the f distribution with m numerator degrees of freedom and n minus k denominator degrees of freedom. If the dependent variable of the unrestricted and restricted models are same, then the above formula can also be expressed in terms of r square as follows: f equal to r square unrestricted minus r square restricted divided by m divided by 1 minus r square unrestricted divided by n minus k, where r square ur and r square r are the coefficient of determination obtained from the unrestricted regression model and the restricted regression model. It is noted that r square unrestricted will be greater than r square of restricted model, and residual sum of square of the restricted model will be greater than the residual sum of square of unrestricted model, or residual sum of square of unrestricted model will be less than the residual sum of square of restricted model. It is also important to keep in mind that if the dependent variable in the unrestricted and restricted model is not the same, r square ur and r square r are not directly comparable, and we cannot use f formula in terms of r square. So now let us discuss an example. The unrestricted regression result is reported as follows. Here log GDP equal to -1.6524 plus 0.3397 log labor plus 0.8460 log capital. T ratio equal to, the T ratio of the constant term is minus 2.7259. The T ratio of log labor is T ratio of the coefficient of log labor is 1.8295, and the T ratio of the coefficient of log capital is 9.0625, and the p-value of the corresponding parameters are 0.0144, 0.0849, and the last one is 00. Here n equal to 20. R square of these unrestricted model is estimated at 0.9951, and the residual sum of square of this unrestricted model is 0.0136. The restricted regression model is given by the following result. Log GDP divided by labor, or GDP labor ratio, equal to minus 0.4947 plus 1.0153 in capital labor ratio. Again here T represents T ratios, P value, N number of observation, and this represents coefficients of determination of this restricted model, and the residual sum of square of this restricted model is 0.0166. You can see that the residual sum of square of unrestricted model is lower than the residual sum of square of this restricted model. So our question is how to test the hypothesis that the economy exhibits constant returns to scale. Since the dependent variable of these two regression are not same, therefore we cannot use the F formula in terms of R square, though the R square values are available here. Rather, we have to use the formula of F in terms of residual sum of square. So from the given result, we can easily estimate our test statistics. So before that, let us write the restricted and unrestricted models in general form. The unrestricted regression model in general form is given by this: log GDP is equal to beta 0 plus beta 2 log labor plus beta 3 log capital plus UT. On the other hand, the restricted regression model in general form is written as log GDP labor ratio equal to beta naught plus beta 3 log capital labor ratio plus UT. Our null hypothesis is beta 2 plus beta 3 equal to 1, which states that there are constant returns to scale, and our alternative hypothesis is that beta 2 plus beta 3 is not or is equal to 1. Now let us define F using the concept residual sum of square as follows. F is equal to residual sum of square of the restricted model. As you know, the residual sum of square of the restricted model will be higher than the residual sum of square of unrestricted model, and F value is generally positive. So this expression will give us positive F value. So RSS restricted minus RSS unrestricted divided by M divided by RSS unrestricted divided by N minus K. So we have these two results. From these results we can obtain RSS value, M, the value of M, N and K. So we have RSS UR is equal to 0.0136, RSS R which is equal to 0.0166, M equal to 1. M is the number of restrictions. In our case, the number of restriction is 1, which is beta 2 plus beta 3 equal to 1. And N is equal to 20. Here is 20. And K is the number of parameters in the unrestricted model. So in the unrestricted model, there are three parameters: the constant term, beta 2 and beta 3. So substituting these values into the formula will get the F value. Here is F is equal to 0.0016, sorry, 0.0166 minus 0.0136 divided by 1 divided by 0.0136 divided by 20 minus 3. After simplification, we'll get the F value of 3.75. Now, let us find the critical F value from the F distribution table. So, we have the numerator degrees of freedom of 1 and a denominator degrees of freedom of 17. So, look, here is the numerator degrees of freedom 1, and if we subtract 3 from 20, we'll get 17. That is, 17 is the denominator degrees of freedom of F. So for 1 numerator degrees of freedom and 17 denominator degrees of freedom, for 5% level of significance, the critical F value is 4.45, and for 1% level of significance, the critical value is 8.40. So we can easily see that the calculated F value is lower than the critical F value. That is 3.75 is less than the critical F value 4.45. Since the calculated F value does not exceed the critical F value at the chosen level of significance 5% here, we cannot reject our null hypothesis that there are constant returns to scale. Therefore, we may conclude that the economy exhibit constant returns to scale. Here is example 2. Suppose that a young Mexican economist was trying to estimate the following model based on the Mexican GDP, employment and capital for the period 1955 to 1975. The researcher was trying to estimate this model. Log GDP is equal to beta 0 plus beta 2 log employment plus beta 3 capital plus UT. The author find the following estimated regression results. Log GDP is equal to minus 1.652429 plus 0.3397 log employment plus 0.845991 log capital, and standard error values are this gives us the R square value of this unrestricted model and this gives us the value of covariance between the estimated coefficients beta hat 2 and beta hat 3. Since we have the value of the coefficients and the covariance of the coefficient beta 2 and beta 3, so we can use the t-test approach to test the to test whether the economy exhibits constant returns to scale. So let us formulate the null hypothesis. These are the null hypothesis, and this is a minor correction. Here will be H1, the alternative hypothesis. So under the classical assumptions and the null hypothesis beta 2 plus beta 3 equal to 1, it can be shown that t is equal to beta hat 2 plus beta hat 3 minus beta 2 plus beta 3 divided by standard error beta hat 2 plus beta hat 3 follows the t distribution with n minus k degrees of freedom, where k is the number of parameters estimated including the constant term and n is the number of observation. So already we know how we have explained how have we got these terms. Now if we substitute the null hypothesis and the expression of standard error beta hat 2 plus beta hat 3, our test statistics will become t is equal to this expression. So here is 1 because of our null hypothesis, and this the denominator expression will comes from these expressions. So now let us substitute the values, actual values from the estimated models. So from that estimated models we'll get the slope coefficient of x2, our labor is here beta hat 2 is equal to 0.3397362, and variance of beta hat 2 is basically uh, the square of the standard error of beta hat 2. So the square standard error of beta hat 2 was 0.1856928, and if we square these numbers we will get this number. So from the estimated model we can find that beta hat 3 is equal to 0.8459951, and the variance of beta hat 3 is given by this value 0.0087146, and the covariance between beta hat 2 and beta hat 3 is equal to this. Now let us substitute all these values into the t ratio t formulas as follows. So if we simplify the expression, these expressions using calculator, we'll get a t ratio of 0.668. So now let us find the critical t value from the t distribution table. So here is a t distribution table, part of the t distribution table. So we have 17 degrees of freedom, and for 17 degrees of freedom at 5% level of significance, the two-tailed critical t value is given by 2.11. Now as the computed t value does not exceed the critical t value at 5% level of significance, we cannot reject the null hypothesis of constant returns to scale. And so we may conclude that the author's claim is accepted, that is, the economy exhibits constant returns to scale. Here is example 3. Please do it yourself, and you can seek support if you cannot go ahead with this example. Here is another example. So do it also yourself. And here is example 5. So here you have to describe several test procedures. So I have listed a set of hypotheses, null hypotheses here, and you have to describe how to test the specific null hypothesis. For example, null hypothesis beta 3 is equal to 0. Null hypothesis beta 3 is equal to beta 4. This basically explains the equality of two partial regression coefficient. So here is beta 5 is equal to beta 6 is equal to 0. Here is null hypothesis beta 2 is equal to beta 3 is equal to beta 4 is equal to 0. Here is beta 3, beta 2, beta 3, beta 4 equal to beta 5 equal to beta 6 is equal to 0. Here is beta 3 equal to 3 beta 4, and here is the null hypothesis x5 has no significant effect on yi. So thank you everybody for hearing the lectures. So next time I'll come with another topics. Thank you.